So here we are studying dynamic games as opposed to simultaneous games. And we can show here that the concept of Nash equilibrium is not sufficient to rule out non-credible strategies. And so you need another solution concept known as subgame perfect Nash equilibrium in order to be able to solve games. And this will lead us to the concept of backward induction as a solution technique. So how do we illustrate this problem? This is the example given in our textbook in chapter 9, which is this entry game, or the textbook calls it a predation game. But you have two firms, and one firm is an incumbent, i.e. it commands a strong market share in a given market. A competitor is trying to decide whether or not to enter the market. The incumbent can respond in two ways. It can either fight or not fight the entering firm. And the payoffs are as follows. And you can see that of particular interest, if firm E does enter the market, the decision to fight is actually costly, right, and results in a negative payoff for the incumbent. If the incumbent accommodates the entrant, it gets a payoff of 1 as opposed to a payoff of 2 if there is no entry, right? So there's a loss of market share, if you like. Now in this game you can easily verify that there are two Nash equilibria. Not entering and firm I fighting is a Nash equilibrium, and entering the market and the incumbent responding by accommodating is another Nash equilibrium. But the claim here is that the first Nash equilibrium here is actually not a sensible prediction for this game. And the reason is that firm E can anticipate that fighting is not a credible threat, precisely because it results in this negative payoff, right? So you can eliminate certain strategies or actions on the basis that they are not credible, because they would not be rational. And once you see that, you can then eliminate the configuration of strategies where the firm enters and the incumbent fights, right? And once you do that, you can see that it makes more sense for firm E to enter the market, because the payoff of 2 is higher than the payoff of 0 if firm E does not enter the market. So actually this Nash equilibrium is much more likely to arise. Now here is a solution technique. You focus on the last decision node and you eliminate the strategy which is not credible. Here in this case, fighting, right? And what you can then do is replace the node by the payoff associated with the strategy that remains, namely non-fighting. And so the game becomes, in its reduced form, the following, right? Where I have now replaced, for the last decision node, the payoff associated with the strategy that is credible. And so on that basis, the firm E will choose to enter the market because the payoff of 2 is greater than the payoff of 0. And so you've eliminated the first Nash equilibrium by solving for optimal behavior at the end of the game. And this is the process of backward induction, which is a procedure that is related to the idea of sequential rationality, where each player is expected to specify a strategy which is optimal behavior at every decision node in the game. Now, backward induction can be applied with generality in situations where games are finite and there is perfect information. So finite games of perfect information are the games in which every information set contains a single decision node and there is a finite number of nodes. And so you can proceed and continue to consider further and further reduced versions of the game, further and further reduced game through this backward induction procedure. Now this brings us to the concept of a subgame and concept of a subgame perfect Nash equilibrium. A subgame begins with an information set that contains a single decision node, and it contains all the decision nodes that follow. We also assume that there are no broken information sets. In finite games of perfect information, every decision node will initiate a subgame. A subgame perfect Nash equilibrium induces a Nash equilibrium in every subgame. So the idea here is to be able to isolate from in our original example, from two Nash equilibria, isolate the reasonable Nash equilibrium, which is to accommodate after entry, and the set of Nash equilibria that can be derived through this backward induction procedure will coincide with the subgame perfect Nash equilibrium. And so the key idea here is really that each action in each of the final decision nodes of the game must be optimal in that subgame, right? So you retain those actions that are optimal in that subgame, and you will solve on that basis, right? So it's a solution technique that you remove those strategies that are not optimal in every subgame, and you solve for your Nash equilibrium on the basis of the strategies that are optimal in each decision node.